Okay, so just to wrap up the last few questions on this exam, I just went out and re-examined the power or energy output from the tidal barrage. We came across this little website. So this looks a lot like the equations we've seen before. So E equals 1/2. Let me go ahead and just write this up here. Tidal E equals 1/2 A rho GH squared. And they screwed up a little bit. That's a P. It should be a rho. 1/2 A rho GH squared. Let's compare that to our energy equation before. Well, if we write it this way, equals 1/2 M is rho V, volume V squared. 1/2 rho volume V squared. 1/2 rho volume V squared. This was for a turbine. That's energy. Now in this case, the A, yeah, so the rho, so if we just kind of pull out the guts of this, so A G H squared plays the same role as V squared. So in the case of tidal, we're basically moving up and down. In the case of the turbine, we're moving right or left. So there's no gravity term in the turbine, whereas there is in tidal. So that's one main difference. We've got that guy, and so if we just do dimensional analysis on this, we've got L squared, L over T squared, L squared, and here we have L cubed, L squared over T squared. So they both check out in that they're both L to the 5th over T squared. It's just that the this height is changing. And I think what we can say is that the height is sort of serving the same role as the velocity, because in the tidal barrage you've got the delta H as the water level goes up and down. It serves the same role as the velocity. It's the same as the velocity moving through the turbine. So now it's much more clear why it's proportional to H squared. That was not clear at all, but you're like, okay, the height's moving, and that change in height has to be proportional to the velocity of the water flowing through the turbine. So, okay, cool. Yeah, that makes sense. Yeah. Okay, so let's get back into the course. Done with exam 3, 5 and 6. Chapters 5 and 6. Then how far have we gotten in chapter 7 and 8?
No.
Not at all. Okay, well, let's dive right in there. Okay, chapter 7, wind. In a lot of ways, the equations that we just did for tidal are the same. It's that 1/2.
Tim covered a brief explanation of wind turbines. I think we were doing a couple of equations having to do with swept area and headwind.
Right. We have, and it's, like I'm saying, we have covered that to some extent already. The power. So I think we're in good shape there. And again, that comes back to Comes back to this guy. Power is 1/2 rho A V cubed. Okay. Let me just pull up these old notes. Let's see what's going on here. Chapter 7 and 8. These are Mark's old notes. So I think summary 3 is behind us. Yes, air has energy. Another thing to keep in mind, and this is one big difference, is that in the case of air, density, something like 1.2 kilograms per cubic meter. So if you imagine, it's weighing the air inside your fridge, weighs a couple pounds, and that's, if it didn't have any mass, then it wouldn't have any energy when it moved. So that's a major point there. The other thing is that air pressure is right around 14.7 psi. It's also the equivalent of about 100,000 pascals, and a pascal equals 100,000 newtons per meter squared. Newtons per meter squared, and so that's just pressure. So 14.7 psi, or it's closer to 101 kilopascals. The thing to keep in mind there is that pressure in general acts the same in all directions. If you're working with a wind turbine, I'm going to draw a super simple one so it's easy. As that velocity hits the blade, the pressure is going to go up, and it is that pressure that creates a force to actually move the thing around. So, we've already covered all that.
So that would basically entail that once you get the propeller going, it kind of helps maintain its own momentum.
Yeah, and that's a really good question. So there are two fundamental types of wind turbine. Let's just dive right into that. Two fundamental types. Yeah. Here's some of the physics. I mean, we've definitely covered all this. Okay, so if we zoom in here just a little bit, it is amazing how many different types of turbines the human mind has conceived of. But a couple different main categories. One is the horizontal axis, and that's the type we're most familiar with, right? That's the one we see out on the big wind farms. You can go 1, you can go 2, you can go 3. You can have your tail downwind. You can have your blades downwind.
That's kind of wild.
Single motor, multi.
Never seen it downwind.
Yeah. Well, in some ways it's simpler because it's the blades themselves are acting like the tail. They're just think of like a streamer on a kite. Multi-rotor, counteracting, crosswind. Okay, so here's one fundamental difference. These are all lift-based, and what do I mean by this? So, lift-based. This is a Darius. And drag-based. This is a Savonius. So in a lift-based turbine, it acts exactly like a airplane wing. So airplane wing, shaped like this for a reason. This is the so-called Bernoulli effect. If I have air coming in from the front, and I've got two little air particles coming in, and here they are as a stream. The easiest way to describe it is that as these go through, as the wing goes through them, there's more space between the dots on the top, and so the pressure, P1, pressure P2, P1 is less than P2, and up goes the airplane. It's also worth noting that this is the lift direction. This is always the drag direction. It's also worth noting that lift is always perpendicular to drag. Okay, so that's Darius or lift-based. Actually, back up one quick second. These are both horizontal, or no, sorry, vertical. Vertical. And yeah, this, I've never seen any of these three in action. But these are actually examples of drag-based turbines. So basically the wind's sort of slapping into that side and spinning it around, and there's more drag. So you're relying on the drag there to smack the thing around. In all of these other guys, you're relying on the lift. The turbine is, literally flying through the air, even though it's stuck to the ground. It thinks it's flying, right? Sucking itself forward is really what it's doing. Okay, so those are all the horizontal. The vertical axis, these are all looking down from the top. So these are, again, drag-based, or as I just said, Savonius. And so as these guys imply, you might have a bunch of, little cups or parachutes at the end.
I think they have one of those outside of the gym.
There is a vertical axis, and man, that thing is neither. It's neither a Savonius or a Darius. Let's see if it's even on this guy.
I thought it was an S rotor.
Yeah, it's sort of a helical S rotor. It's a helical S rotor.
And it's also got a little solar panel on it.
Yeah, I think that thing is powered. I mean, I've seen it spin. I'm almost not. So Brian Kearns was asking me, about that, and we kicked it back and forth a little bit, and it's a little bit of greenwashing, and I hope this bigger solar thing happened, but
I'll get more details on it.
yeah, I'd love to have it because, gosh, Kearns he started this energy technology program, and just beats his poor little head against the administration endlessly because he was looking for even just permission to solicit, gosh, it was in the order of like $5 million to do big solar, put maybe a 1 or 2 megawatt array right here on campus, and facilities like, no, we don't want to clean them, it was just all this weird resistance, like what? And so
Students do.
well, it's just kind of weird political gridlock for no reason, but he was able to get that little doodad installed, so
Just
and it's good.
imagining having a bunch of those everywhere. I mean, they're aesthetically pleasing.
Yep.
They're not giant and
Yep.
like offensive.
Well, there was another plan. me show you this guy. And here's how we can sort of get ourselves into trouble sometimes. So I love the looks of this thing. You know, looks like
Yeah, those things are so.
looks like a tree. So it's expensive, right? And it doesn't make a whole heck of a lot of energy. So former President Engstrom and current Mayor Ingen were kicking back and forth. Hey, shouldn't the University of Montana have one of these wind turbine trees in front of its new building? Because the architect didn't want the old one, blah, 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 whatever. And Brian Kearns actually killed this thing. He said, no, the payback is too long. I'm like, well, wait a second. You know, if you drop 50 or 100 grand on this tree and you get one or two students extra because they like the wind, the payback's instant. So, you know, just thinking everything in terms of, you know, engineering and hard numbers isn't always the most
That's the
effective way.
curb appeal. Alternatives
Yeah.
is almost always drastically more attractive
Yep.
than the curb appeal of fossil fuels.
Well, yeah.
I see so many people from my generation and beyond millennials, you know, they're so hopeless and depressed because
No, they are not.
corporations they're just ruining. You know,
There are
just-
good corporations and bad ones.
I know.
Yeah, so.
All of a sudden they're inheriting a world that's just, you know, very grim.
Well, we're-
oh no.
We're going to change that, Rob.
Yeah.
Don't you worry. We're going to change that.
So,
Actually, tomorrow, I think.
Yeah.
I'm on my way to
Yeah.
Billings. I'm going to change
Change it
that.
tomorrow. But you have a good point. You know, the appeal beyond the functionality and the profitable margins is always.
Yeah, well, and like you said, too, you know, once corporations, whatever, manufacturing firms, you know, start to go this way, it builds on itself in the same way that we're seeing Tesla,
Well, I
so.
think Trump might actually have a longitudinal positive effect.
Mhm.
Because what he's
Yeah.
trying to do right now is going to fail so massively
Yeah.
that everyone's
Yeah.
going to be like, this is ridiculous.
Yeah, yeah. No, I hear you. There's the, I think it woke a bunch of people up.
Yeah,
So,
it really
yeah.
is. It's kind of like, I think it might have a homogenizing effect with people who really do want to kind of get past this whole 20th century mindset.
Yep. No, I like, that's a good word for it, 20th century mindset. Yeah. So, you know, right there, yeah, okay, it's expensive, but, you know, it sends a message, and it's doing something, it's making energy, you know, it's better than just nothing sitting there. No, I love these things, so maybe we'll get one going one of these days.
Money flows through trees.
All right, well, we got 10 minutes left here. What else do we want to hit? Page down, come on. Old school. This is a windmill. That is not a wind turbine, that is a windmill. When you hear people call the machines up at Judith Gap windmills, they are wrong. They are wind turbines. A windmill converts mechanical energy into other mechanical, so pumping or grinding, what have you, versus making electricity. And here's one other idea, and this is what I don't care. It's the brave new world of the internet. What I really want to do up at Judith Gap, so Ryan Carson, one of my grads, works up there. He's Iraq war vet. Now he's making a really good living up in Arlington. A lot of times they'll have more electricity than they can use, and it gets it turns into a little bit of an issue. But what I would like to see happen is when there's excess wind, just start running air compressors. So the air compressor, it acts as a brake, in the same way that electrical brakes work in the Prius, right? So you've got this load, you've got an electrical load, and what air are you going to compress? Well, the air. You start compressing air, and once you compress air strongly enough, you do a couple things. I mean, you just store it as energy. I mean, right there, compressed air, not very high density, but that's happening with some of these large mining operations. But nitrogen and oxygen are both commodities. You see nitrogen trucks and oxygen trucks drive all the way. You also know you're going to bring some CO2 along for the ride, so you're sequestering CO2. There's also trace amounts of argon, helium, et cetera, et cetera. So there are all kinds of, commercially viable gases. So you've done energy storage, you've sort of solved the overburden problem, and you're making commercially viable gases, and sequestering CO2, which you then,
It's clean air, we can sell it to China.
Yeah, we can sell the clean air to China, yeah.
Fresh mountain air.
Yeah. Yeah. Again, windmill used for pumping. It's kind of your classic.
That's all they did there, the windmills were just pumps?
Either pumps or for grinding, grinding mills.
What were so in Holland, they've had over hundreds.
Yeah. Holland's underwater. I mean, I don't know what the average sea level of Holland is, but for gosh sakes, I mean, that bad boy is it's like New Orleans.
Yeah, they have the most advanced levee system.
Yeah. So, yeah. And, grinding grains.
It'd be pretty interesting over the course of the 21st century if Holland's infrastructure became kind of commonplace. The sea level rise and everything like that.
Yep.
But they do have the model.
Mm-hmm. Yeah. And there's a few of these sort of high-end permaculture towns popping up in Holland too, which that was part of what I was doing there in California. So yeah, I think we're going there.
It's exciting.
Yeah. So there's double, triple, single. The idea here, you look at this thing, you're like, golly, there's a lot of wind blowing past this thing that I should be using. Well, if you have a lot of blades, think of it this way, a lot of blades, this is sort of a low speed, high torque. This is like your first gear, basically. If you start to move up into just one blade, this is more fifth gear, high speed. So this blade, obviously it can only be one place at a time, but if you have a whole bunch of blades, they're kind of interfering with each other. Yeah, you're interfering with each other. So the triple blade seems to be the sort of happy medium for balance. One issue, and this also comes up, one issue, the double blade, you kind of get the Dorothy Hamill effect a little bit. I don't know if you've like professional ice skating where ladies hold their arms over their head, and so as your arms come down, the angular velocity changes. So as these blades rotate, the angular velocity of the entire structure changes, and you start to get some shimmies.
Yeah, it's pulling on each other.
Yeah, especially as this guy spins about its vertical axis. So as the wind changes, now I'm over here. And I think there's an exam question on that too.
Yeah.
It's sort of an example of why you might not want a two-bladed design. And you can think of this guy, think of the three-bladed bad boy as more, I think of it more as like a three-phase electricity, just smoother delivery. These are kind of old school Darius, however you want to pronounce it, turbines. One issue, like if the wind's just kind of blowing right through the middle, they don't self-start. So sometimes they have to have a little motor to kind of kickstart them and get them going. But they are lift-based, not drag-based. They've got little, and I built one of these with some students back at Drexel, and we got the bad boy spinning. And the whole reason it's shaped like this is it's sort of a fail-safe mode. I don't know if there's a picture. Yeah, these guys. This is the type we built. Spins fast enough, it just blows itself apart. This whole fin will just crack off. And we got spinning fast enough that we did, in fact, fly apart. It's kind of wild.
That's what I've seen that on YouTube.
Yeah, turbine failure.
So if it's shaped like the spherical shape, it sends some of the excess force towards the inward.
Yeah, so in this case, this whole member, as it spins, this portion is in tension, which is sort of a favorable loading mode, whereas when this guy starts bending, it's in bending. So just you're more or less taking your pencil and snapping it like that. Much easier to break a pencil like this than it is like this. Yeah, yeah. These guys, little different, still, you might call these hybrids. They're still lift-based because they've got airfoils on there, but perhaps a little less prone to failure. If they bend, okay, fine, they just kind of bend a little bit, but they're not going to snap. Okay, as I mentioned before, lift and drag are always proportional. If you're throwing a pair through the air, the drag is much greater than the lift, and the thing tends to fall. However, if you're flying an aircraft, your lift is much greater, and up, and away we go. So these are, this is a naturally evolved system to move through the water efficiently, engineered system for moving through the air efficiently, and here's your wind turbine. Same
An example of biomimicry.
Yeah, a little biomimicry there, sure. This is Bernoulli's principle I was showing before, where these guys on top get a little more spread out.
When did he figure that out? Was it
Bernoulli?
Yeah, was that pre-Wright brothers?
Oh yeah.
So did they actually use?
The
Wright, or did they just take a guess?
The Wright brothers more or less took a guess. The Wright brothers were not mathematicians. They did, however, there were a lot of weird counterintuitive things happening. In fact, in 2003, in that centennial, I served as one of the volunteers in the park. It was kind of why John Travolta was there. But one thing that was somewhat counterintuitive is that their little struts were rounded off squares instead of ellipses, which was a little bit strange. They also built one of the world's first wind tunnels, and then it was the wing warping that actually gave them the control that the other folks weren't getting. Where one wing would warp up and the other one would warp down, that gave them the ability to actually stay in the air for a long time. But no, I don't. Gosh, I've seen the Wright Brothers Museum and all that. I don't remember ever seeing a single equation. Nah. Yeah, just looking at the birds and using their whirligigs and kites, and yeah, it was all kind of seat of the pants.
It really does surprise me that was never done in antiquity. Not to the point of the actual takeoff,
Yeah.
but a glider, if you will.
Yeah.
The
Well,
technology talks about it.
yeah. I'm not sure what the fabric tech, because the Wright brothers use canvas, and I don't really know what the fabric technology would have been like, and then just you got to have a certain amount of machinery, and yeah, but you kind of would think that some kind of glider, and I know Da Vinci built some, or designed some. I don't know about built, but yeah. Okay, so here's your negative pressure. So here's your wind coming in, and sort of the more the more curve you have, the more uplift, negative pressure you have, suction per se, versus positive pressure, and this is really what drives the entire wing up, or in the case of a wind turbine, forward. Okay. Well, we got through the first third of wind. Let's just see what else we've got. Let's just see what else we've got here. Okay, 7, 8. So we have 4 chapters left. We'll do 7 and 8 this week, and next we'll do 9 and 10 the next 2. And I think that's the end of the semester.
Yeah, pretty much.
When's the last day of class?
Finals week starts on the 8th.
Okay. So here's chapter 8. Here's chapter 9. No, sorry. What's wind? 7? Sorry. Yeah. Here's chapter 7. Here's chapter 8. Here's chapter 9. Here's chapter 10. That's it. Got 4 weeks left and 4 chapters, so we're right on it.
Yeah.
Don't forget to let the cat out. Neighbors leaving town, gotta make sure the cat gets let out. Okay, thanks, thank you, that was good. I'll look for that one last, I think the summaries are in good shape, and I'll look for that one last problem set for you.
Yeah, there's 2 assignments. I don't know which one.